industry for a long time and a veteran teaching faculty across all IITs and IIMs. And to moderate the session, we have eminent nephrologist with us, Dr. Seerapani. Welcome both of you, sir. And over to you, Dr. Mahesh, to educate our doctors on the intuition for the clinicians and how the missions have to learn.
Sure, sir. Thank you so much, Dr. Suresh and Dr. Pani, for hosting me today. Really happy, and I hope we get to learn from each other as well. I'm new to this field, so I also can learn from all of you in the end discussion, right? So the agenda for this session is how machines learn, intuition for clinicians. So how I planned is to have this session split into two. The first half can be a little bit technical because I want to intuitively let you know how these machines are learning, right? So we can draw parallels to how we as humans learn. So we see something and we learn from it. It's not that different how these machines learn. We can draw parallels. So that will be the first half, a little bit maybe technical. And the second half, let's pick a case study. And this was one of the opportunities I had a few years back to work on a healthcare case study. So I'll take you over the problem statement and how we went about solving it. And it is also a published work, so you can read further on it as well. And then in the end, we can have some Q&A. So that sort of is the agenda. So we can get started, right, in the interest of time. So let's first try to understand how these machines learn, right? So what we see in the slide is, of course, an image of Mahendra Singh Dhoni, right? So what we see is MS Dhoni and with a bat, with a yellow color jersey, and we recognize that's what from the image, right? But what a machine sees if we give this image is just a bunch of numbers. That's all. So a machine does not know a cricket bat, does not know yellow color, does not know MS Dhoni, right? It can only understand numbers, and it has the capacity to do some operations on the top of numbers. Then how does the machine learn, right? So to give an intuition, in the right top corner of this image, we can see a number 8, right? So the number 8, we can see it alternating between number 8 and a matrix full of numbers, right? So when we take a picture using a mobile phone or a camera, we see something like 1080 pixel or something like that, right? So which generally means it's 1080 cross 1080 matrix, okay? I'm just doing a check. Am I audible and is my screen visible? I'm just doing a check. Hello?
Very much audible and visible, sir.
Okay, so sorry, something happened in my screen. That's right. Okay, so we see a number image, right? So at the end of the day, it's a matrix of numbers. If it's 1080 pixel image, it's going to be 1080 cross 1080 set of red, green, blue, and all those values. So how?
Your image is not, your screen is not being shared.
You need to reshare your.
Okay. Is it? Let me try it again. So. Okay. So. Okay, fine. Are you able to see your desktop?
Yeah.
Is it visible? Okay, fine. I brought my slide. Let me start from where I left. And is it fine now?
Okay. Absolutely, yes.
Okay, thank you. Yeah. So we have this number 8 and it's alternating between numbers, right? So an image, what a machine sees is a bunch of numbers, but what we as humans see is totally different, right? So that's the foundational difference I want to see. So now how a machine then learns if it just sees a bunch of numbers? You can see in the top right corner, you see some values between 0 to 255 all across this matrix, right? So whenever you see a big number like 255, 250 and all, those numbers are usually aligned between where the number 8 is written, right? So that's how it is. So what we can do is you can clearly see the pattern. This area has a lot of numbers. So I have a bunch of images like this translated into matrices, and I'm going to tell literally to the machine, image 1, we call something as 8. image 2, we call something as number 2, and so on. So the machine knows that if these positions of the matrices has numbers greater than 200 or so, it can be classified as a number 8. And if the other positions have a set of values written, it can be classified as a number 2. So that's how a machine is learning, right? So the takeaway from this slide is machine at the end of the day, irrespective of the input, be image, audio, video, whatnot, it just needs a bunch of numbers. And when we teach the machine, hey, these sort of numbers, this is what it represents, it learns over iterations. So that's the end story, right? So formal textbook definition of AI is something like systems that think like humans and think rationally, also systems that act like humans and act rationally, because thinking and acting can sometimes be a little bit different. So that's the textbook definition of AI. Now, we understood everything is a bunch of numbers and machine tries to learn over iterations. So what I'm trying to do now is, what exactly is that learn, right? It's definitely not magic, or it's definitely not something like as complicated as rocket science. It's actually simple intuition, right? So to give that intuition, I'll just take an example. So let's assume I have a table where I have written number of patients visiting a hospital, right? So I have a book, I have just written Sunday 200 patients came, Monday 90 patients came, and so on. So now by looking at this, the objective here is I have to predict, given a day of the week, how many patients will come to the hospital. So maybe I can plan the queuing and other optimization and things like that, right? So just as human, how we look at the table and interpret, okay, we have Saturday and Sunday, that seems to be a weekend. So we bring in this perspective of something called as weekend because we know this. So we say that this is a weekend. And then we have some other days, we classify them as weekdays. So these are all from our knowledge of our past, right? And then we do that. Let's do the same. Now I'm going to do that flag because I have this knowledge. I'm going to let it know that it's a weekend, it's a 1. It's a weekday, it's a 0. Now my job is I have to predict how many will come. So just by looking at these different data points, subconsciously what we think is, if it is a weekday, it's going to be a lesser number. If it is a weekend, it's going to be a higher number. That's what we subconsciously, our brain is processing by looking at it, and that's how we interpret, right? Now, if I ask a machine, it just sees a bunch of numbers, 1, 0, 0, 0, and all the way 1, and 200, 90, 85, all the way 180. So what the machine does is, us subconsciously doing it, it outputs me a formula. It says that the number of patients, what you can do, Mahesh, is you can just say it's 95 plus 110 times whether it was a weekday or a weekend, right? So if we do the simple math, what happens? For example, here 95 plus 110 into 1, because it's a weekend, that's like 205. That's what I predicted. Other days, I just keep telling 95, 95, 95. And then if it's a weekend, I just keep telling 205, 205, right? So this is how I do it. So of course, I am not perfect. This is not God, right? This machine does make mistakes, but more or less it's nearby. That's the point, right? So subconsciously, we had a pattern where weekday lesser, weekend higher, that got translated into a mathematical equation. And then you just substitute there, it says that weekend higher, weekday lesser, right? So that's the biological path and the empirical path towards learning, right? So this is exactly what is happening. When I give dozens of data to a machine and literally tell, this is what happened on a Sunday, this is what happened on a Monday, over time, it comes up with this magic equation with these numbers 95, 110 and all, and then it gives me, right? So how 95, 110 came is a matter of several iterations and complex maths running in the background. So that's what is technically statistical learning, right? So I can call this equation as some mathematical expressions, but this is what is happening at the end of the day. Right? So technically, these are called parameters, right? So to find the number of patients just by using weekday or weekend, it's a 2-parameter model that I have. So parameters are nothing but this 95 and 110, some sort of numbers learned, right? Now, what is something as complicated as a ChatGPT doing? To draw parallels, here we are predicting how many patients will come. What a ChatGPT is doing is, given a set of words, what will be my next word? So So if I say that I am going to fill in the blank, from the internet, it has learned a complex math like this, and it does all the operations, and it predicts that I'm going to should possibly be followed by a school, right? And then it takes I am going to school and predicts next. It's a full stop, and then so on, right? So here I told a simple example where there are just two parameters, but something maybe a chat GPT, which is also called as a large language model, can have in the order of billions to trillions of parameters. So imagine how much mathematical multiplication happens just to come up with a prediction. Right? So this is one intuition of how a learning happens given a set of data set. So I'll just take 2-3 minutes to give another intuition of a different set of problem altogether. Okay. So this problem is I have a set of patients, and let's call that patient as all the way from A to G. Okay. So we have all the way from A to G 7 patients, and each of them we have some measurements, a V1 and a V2, right? So any data that I'm sharing, right? So this is all just some simulated or synthetic data for educational purposes. So this might not even make practical sense. This is just for a demonstration. Okay. So I'm just sharing some numbers, 3, 4, and 5, and 2, 5, 7. So I have 7 patients, each of them given some measurements, any measurements. Now my job is to find which 2 patients are very similar, which 2 patients are very dissimilar, just by looking at the data. So what I can do, I can manually see E and F. I can see that this person has a 6, this person has a 7. So when I technically take a 7 minus 6, it's actually 1. But when I say A, that is like a 3 minus 6, right? So that's like a lot of difference compared to a 7 minus 6. So like this, subconsciously, we do something in our brain and we figure out that E and F seems to be very, very close and A and F seem to be very, very farther. Right? So that's how we interpret by looking at this table. So we did this subconsciously because it's simple numbers. We all are very much experts in very simple arithmetic, subtraction, addition. Our brain did that subconsciously and it told you that E and F are similar, A and F are similar. Now, imagine I can give you something like this, but instead of 2, I can give you maybe 100 measurements. And now with respect to all these 100 measurements, I will have to figure out who are similar, who are dissimilar. Right? Now that becomes a little bit cognitively heavy. We cannot simply do that. Right? We need some math formula. So that's exactly what happens. So what I'm going to do here is when I have multiple numbers, I have some mathematical formula which gives me the difference between those set of numbers. This is another set of problem, right? So what I can do is I'll show you a table. I have literally taken every patient with every other patient and computed those numbers. What the difference between those numbers. So if you see here, this one is the lowest. And if you go back, why? Because E was 6,6, F was 7,7. So I have literally subtracted and that did some simple, let's say some math. Ignore the formula. I'm just telling you, which is square root of 1 plus 1, which is square root of 2, which is equal to 1.4. So this is exactly how I computed this number. Now, like this, I have done with every patient, with every other patient, A versus B, A versus C, A versus D, all the way to all possible. And this, I can say that this is the most similar pair. And the farthest pair is this, because this is the biggest number. So the farthest will be an A and a F. So when I go back to this slide, I can see that E and F are the similar. And I can see that A is 3,2, F is 7,7. They are the farthest. Right? So what we did, again, biologically in our brain, we have a mathematical proxy and we apply that and we come up with it. Right? So what are the learnings so far is we have 2 types of problems in learning. One, we are trying to predict something. While trying to predict something, I show the answer, I teach the model, it gives me a math function. I just substitute, I get the answer. That is one type of problem that we have. Other type of problem is I don't have the answer. For example, in this data set, I have no idea who is similar, who is farther. Nobody has told me that. So I myself took a deep dive into the data, looked at all possible differences, then concluded E and F could be similar, A and F could be farther. So both are two different schools of thought, and that's what I mean by two different types of learning, right? So this is another example. I have some patient vitals, again, demonstrated, very synthetic data, does not make any sense. So I have a patient here, you can see who has some, let's say, sugar measurements and age, and I'm going to literally compare patient 1 with patient 2, patient 1 is patient 3, all the way up to patient 10. I do some math, and I figured out that patient 10 is the most similar compared to patient 1. And then I find that, right? So now, this, if we think from how we learn, right? So that covers the first part where we have the intuition. So when you think of how we learn, how I learned in my college, how all of you might have learned in your medical school and all, it's sort of parallels. You, as a student, would have gone through several ECG reports, several medical reports, and an expert doctor would have taught you if cases like this are there, then this is how it is. And then you learned. Here, what is happening, the parallel, I am giving a set of ECG reports or something, images, and the doctor is also telling this sort of image could be a tumor, this sort of image could not be a tumor. But how we learn is consciously, cognitively. How the machine learns translates that into a bunch of numbers, and it comes up with a function and tells you the answer, right? So it's sort of very similar, but here it's an empirical way of learning, but how we learn is sort of a biological way or a different way of learning, right? So now, this, whatever this we discussed, right? It's called a supervised learning, okay? So supervised learning are those types of problems where I can tell you the solution as well from the past. We can take a very simple example of scan or some sort of report and a medical diagnosis. So I can give you the report. I can also tell you what was the diagnosis of this report. A doctor can literally go through all of these and create a data set, maybe hundreds and thousands of patients' reports, and individually what the diagnosis is. Now, literally like a university, we can teach a model when this is like this is how the output is. And we can also see if the model is making mistakes because we know the answer. If it says that it's not a tumor, but from the answer we know that a doctor said it's a tumor, we know the model learned it wrongly. So we can supervise, literally teach a model, and that sort of problems where we have the solution as well in the past is classified as supervised learning. But let's assume which patient is similar to which patient, right? Nobody has looked at all the patients and told me these two people are similar. I don't know the answer. I'm going to do a deep dive of all the patients out there and figure out who would be similar, right? So I cannot supervise whether it is correct or wrong. So such sort of problems are called as unsupervised learning. So now our job is to find what type of problem fits into what type of learning, right? So that's what we are going to see. Now moving to the second part slowly, right? So where typically, right? Typically today solving problems by writing a code, it's already becoming outdated. The best programming language today on planet Earth is English. Okay. So as of today, we need not literally write a program in any language. We can literally just talk, hey, I have a bunch of patients, help me find similar patients. That's all we can say in English, and we have machines to do that for us automatically, right? So then what is exactly important is how we formulate the problem, and that for formulating the problem, domain expertise plays a very key role. So for example, I can be given a bunch of data set, open source data set, and asked to do some exercise in medical domain. But I am totally new to healthcare and medical. I might not be as knowledgeable as all of you. So when I try to solve this problem, and in the other case where I sit with a doctor, try to understand how maybe in this case this diagnosis works, and I formulate a problem, that's like the best problem. So formulation, we need domain experts. I'll give you a very simple example. So again, simulated data set, synthetic. So we have a patient, 3 patients, and I have some measurements of the patient. Okay. Now, option 1, a doctor can go through this, and with their expertise, they can say that this person is diabetic, this person is not diabetic, so on, right? So then I will teach a model. This is how it works, and the model learns. This is called a supervised learning. This is what we saw. I can formulate this differently. I don't want to believe in the diagnosis. Okay, I will just pass this data, and I just want to group patients who have similar vitals. That's all. I don't want to know whether it is diabetic or not diabetic. I just want to do that. Then manually, I will look through all the patients in group 1, all the patients in group 2, and then I understand what sort they are. Okay, someone could be highly diabetic, another group could be mild, and so on. Right? So I can formulate the same problem using an unsupervised way as well. Both of them are correct. But which one suits you? That a decision a domain expert has to take. In some cases, I don't want to classify diabetes. In some cases, I want to just understand the different levels at which diabetes plays a role. So it's from the doctor or from the domain expert, they come up with this formulation. So the art of formulation is the creative part here, which it's still with humans, fortunately. And that's where we have to play a very significant role. So, okay, the last part, any data that we have in AI ML space, we can classify it into a structured or unstructured. Definition is very simple. If something is all well tabulated and numerical, an example is just vitals, right? It's a structured data. But if I have non-numerical things like images, text, audio, video, those sort of data is highly unstructured data, right? So based on the type of data, some algorithms work better, some algorithms does not work better. Okay, so unstructured data is very, very highly complex. Even us as humans, we find very difficult to understand English sarcasm or trying to identify an image, right? So it's really complex even for us. So it's much more complicated for a human. Right? So unstructured data is generally very, very highly complex. So traditional algorithms, they fail when we use unstructured data. So unstructured data very, very highly works in this world of algorithms or family of algorithms that some of you might be already knowing. It's called neural networks. That neural network family of algorithm works very well with unstructured data. For example, we unlock a phone with a face today and all those things. It's all powered by these complicated family of algorithms based on neural network. So just a field dedicated only for neural network, that is called as deep learning. So that's the last definition for the day. So deep learning is a field that purely focuses on neural network, different types of neural network. So some neural networks work with text, some neural networks work with images, some neural networks to work with sequence and videos and all that. So there are specialized neural networks for different types of data. All packaged together is the deep learning. So the takeaway at this slide is, if something is just structured in the problems that you are solving, maybe traditional algorithms, machine learning works pretty well. But if your problem statement is to do with more complex data like images, audio, and all sorts of things, video, we have to rely on complex family of algorithms like the world of deep learning. Okay. Now I'll go, one summary here. So we saw that supervised is one family of algorithms learning where we know the answer to the problem that we are solving, right? And if the answer is something numerical and continuous, we call it regression. If the answer is something yes, no, or category, we call it classification. Example is number of patients next day is regression. Whether a report is positive or negative is a classification, right? So that is one school of problems where we know the answer that we are going to solve, it's supervised. But there are some schools of problems where you want to formulate it in a way that I don't know the answer, I want to figure out the answer, right? So then that is called as unsupervised. That's the family that we're talking about. And then we also classify based on the types of data. If our data is numerical, well and good. If our data is very highly complex and unstructured, like most likely medical field, I believe, has rich unstructured data. I could be wrong, but that family of algorithms are deep learning or neural networks, which are specialized in images, video, text, and all those things, right? And then today we have something on the order of ChatGPT sorts. which is also deep learning. So the T in ChatGPT, as some of you know, it's generative pre-trained transformer, right? So transformer is one particular family of neural networks that does extensively well with text. So that is also a neural network. At the end of the day, it's deep learning, right? So now we'll pick up a case study, which I got an opportunity to work. And I want to draw parallels of that case study to something like a ChatGPT. Okay. So as you can see, these are machines. I like this image because someone says, call me a cab, and it says, hi cab. My personal opinion is I do not blame the model or machine here. It did a fantastic job. Just that we have a social construct, right? If I have said that, call me a hero, and it says, hi hero, I would have been unhappy. I'd have been very happy. But I said, call me a cab, and it says, hi cab. I got disappointed because I have a different expectation. When I say, call me a cab, I expect the AI to open the app, book a cab for me, right? So, but from a machine perspective, it's a bunch of numbers, and it learns that when someone says, call me something, you have to call them something. So the machine did its job, but we find a misfit, right? So that's what happens even in the real world. So when you as doctors are working with the system, several places, I'm pretty sure you will find that this does not make total sense. But we have to just understand that it's just translating things into a bunch of numbers and trying to assist us with a recommendation. That's all, right? So that's something we have to do. So I'm going to draw parallels to a ChatGPT. So what I'm going to do is, how a ChatGPT works is it tries to predict the next word. That's all it does, right? So when you see hi, then it predicts hi how, and then hi how can I, hi how can I assist, hi how can I assist you, question mark. So that's how it goes, right? So it's basically predicting what comes next. So if you ask something like what is 2 plus 2, natively what ChatGPT does is, in the internet, most of them would have told 2 plus 2 is 4, so it says you 2 plus 2 is 4. But another way to solve this problem is opening a calculator, putting a 2 and a 2 and doing an addition and finding that the answer is 4, right? So that is another way of doing. But how natively a ChatGPT does is, it tries to predict 2 plus 2, usually in the internet is a 4, right? So that's how it is working. So let's take this model, a complicated neural network that is specialized in predicting next word, preferably English. A bunch of English words are given. The entire internet is given as teaching reference. It goes through the internet while training. It learned whenever this word comes, this is what comes next. So it has a very good knowledge out there. Now, what I'm going to do is translate this very similar problem to a medical use case. So I'll just go to that image and come back here, right? So let's take this example. I have a set of words. I teach something like a ChatGPT. Whenever someone says the patient has the most likely used word is fever from the internet. So it predicts that it's fever. Now imagine I have claims data and some EHR data, health records data, electronic health records data, and I have several medical events happen to a patient over time, right? It could be even as simple as purchasing a paracetamol from a pharmacy, consulting a doctor, taking an X-ray, doing a scan, did a surgery, had a diagnosis, took a second opinion to a different doctor. So if in a world everything is claimed, insured, and or if the person is visiting the same hospital, the hospital would have track all of this data, right? And each data, at the end of the day, machine needs a bunch of numbers. That's all. So what I can do is, there are some international standards. All of you, I'm pretty sure, right? You all are the experts in this. So you might have heard about these codes, right? So we have ICD-10 sort of standard codes. So what I can do is, let's assume this is again synthetic and made up data, okay, purely for educational purpose. So lower back pain, I can call it something like an M54.5, and then something else and something else, right? So for a given patient, I can create lots of sentences. How the sentence looks like in this case, for this patient, M54.5 followed by 17.9 followed by G56.01. So that is just one sentence talks about this patient, which literally means these are the most recent codes or medical events that the patient engaged with in that order. Now I can give these sentences to something like the same neural network that is like a chat GPT. So what happens when I give a set of words, it predicts the next word. Similarly, here I create a sentences for patients, but I put some ICD-10 codes. So by reading it, it does not make sense. It will be like a bunch of codes, but at the end of the day, machine does not care, right? It's not about the grammar or the language. It's about a set of words come together, then next words come. That's how it learns. So what it learns is, it learns that usually a 5.4.5, 17.9 should be followed by a 5.6.01, majority of the patients. That's how it becomes knowledgeable. Now, when I do this, what happens is, this interesting problem that I told, this is exactly what we did. So it was one of the biggest pharma companies in the world, and we have to literally forecast how many dosages of a particular drug would be prescribed, the demand for a drug in the, let's say, the next year or so. But the demand for the drug, the same problem if I translate to something like an Amazon, what is the demand for TV sales? How I do it is, I take all previous year TV sales and train a model. It predicts that, okay, usually, Diwali time people buy TV, so it has some seasonality and all those things. But here I cannot say that if something it's like a cardiovascular or some sort of drug, I cannot say that, okay, June time, usually people get more cardiovascular drug. No, that's not how it is, right? So this problem was translated to a treatments modeling problem where we take patients' classified data and we try to model how many patients have the risk of a particular medical event. Let's say my drug could cater to a particular medical event, XYZ. So I take all the previous events and try to predict what will constitute this event, right? So I might have 1,000 patients. For each 1,000 patients, I might have about most recent 100 medical events. And now using most recent 100 medical events, I'm going to teach a model. If I have 100 patients, patient 1 had this particular diagnosis. Patient 2 had the other diagnosis. And patient 3 is healthy, no problem. Patient 4 is healthy. So this model will learn and it will try to predict, given a patient, which all patients have higher risk of this particular diagnosis that I'm interested in. Now, I know how many patients, let's say in the next 6 months, are at the risk of this diagnosis based on the medical history. And that is a proxy for what is the demand for a particular drug, and a particular doctor has to be prepared for that. Right. So drawing parallels, this is where the formulation helps. So this is not natively formulated. Someone knows that this is how ChatGPT, let's say, works. Now you are architecting this problem as a domain expert and saying that, why not I create sentences out of medical codes? Because all that you care about is a set of codes should lead to the next code. The order is all that matters. Meaning does not matter. So you translate this problem and then you get the solution, right? So that's why I said it's the art of formulation. The formulation cannot be done by a non-domain expert, because only a domain expert knows what sort of data, what sort of nuances exist here, and they can come up with this prediction, right? So to summarize, just a quick recap, right? So we found that problems can be split into something like predictive or something like not predictive, right? So that's how it is. So sometimes all I care about is finding similar groups. I don't want to predict anything. The second we learned is data can be numerical or non-numerical, structured or unstructured. If it is non-numerical, the best to go to is some complex deep learning neural network algorithms. Other algorithms might not work well. So first we have to find what type of problem is it. We have to formulate and then find the right toolkit for it. And then formulate, find the toolkit. Then it's today just wipe code. You literally don't do programming, nothing. I just go to a machine like ChatGPT and say, this is exactly what I want. I have a bunch of diagnoses, take the ICD-10 code, create sentences, try to predict the next code, and then do it. It will do it. But this formulation, I should be doing it. That's where my value add will be, right? Yeah. So this is one such case study. So we did this work. This source you can use. These papers are available open source. So it's a work that we did where we took these medical diagnosis codes and tried to predict within 30 days if a patient will be readmitted into a hospital or not in the United States. You might be knowing, all of you, like there are some acts, right? The hospital readmission reduction program and all. So where the you want to reduce the number of readmissions happening within 30 days for a selective set of diagnosis. Otherwise, the hospitals will be penalized. They have a penalty like 1% of their total medical treatment revenue and so on. So this paper focused on that gap. We tried to predict if a patient will be readmitted within 30 days. If it's a high risk, then more expert senior doctors can review them before discharge so that a mistake is not a possibility, right? So at the end of the day, this is not a machine making a decision, coming up with a suggestion. A human expert is out there who is looking at it and taking a second thought, because a senior doctor cannot attend to maybe all the patients out there. So we prioritize patients based on this toolkit, and then a doctor again takes a call, right? So this is one such work. You can see everything, all the details are present in the paper. Another source I would all like to point you to is you can again take this, an open source version is available. So this is a very nice source. It's available, a guide to deep learning in Nature Medicine. Some of you might have read. So they give several approaches towards how we can take EHR data and these sort of ICD codes and try to, understand how some symptoms influence a disease, right? So more research or more sort of application towards that is discussed in this particular paper. And again, I'm just pointing to these references. So if you are interested, you can just read through it. This is again from the same paper, how this can be done for genomics and all. And some use cases that I had an opportunity a few years back when I was working in healthcare is drug discovery, somewhere where we extensively used unsupervised learning, because I don't know the combinations. I cannot try out all combinations. Maybe I don't have the time. So it's an unsupervised. You just find groups and target some groups which might have the magic combinations, right? So drug discovery, usually unsupervised. And electronic health record analysis that you can see here. Here, this is more of the use case study. I said, I have a set of past medical events. What will be the next event? Very similar to a chat GPT, just that the sentences are ICD-10 codes. And image diagnosis, most widely used healthcare application, right? We have dozen of tools. So how to prioritize scans and all. And then clinical natural language, how actually I automate a lot of things, right? So recently I took my mother to a hospital, and then she had some junior people who are asking some questions, taking some vitals, and doing a study of her. So the senior doctor has more data points to actually talk to her, right? So these sort of places are where these sort of natural language processing tools come in very handy. They can document things and all those things, and also creating software or tools or dashboard where you can find similar patients. And another interesting project is like when you file a drug from a pharma perspective, right? You have the FDA, the proposals and all, which will be like 800,000, 2,000 pages. So for drafting that, for reviewing that, what is the risk that this will be flagged by a reviewer? Because most comments from a reviewer in the proposals are, when I went through those, which could have been controlled by submitting itself, like asking results in a table, putting some statistical things on clinical trials. So these could be much more avoided, and some LLM based tools can help us audit, right? And the last interesting project is a lot of patient feedback is gathered by doctors, right? Which could be interviews or audio transcriptions. And these could be analyzed, and these sort of patients get this side effect. These sort of patients do not get this side effect, right? So such sorts of analysis and all those things. So at the end of the day, any problem we take, we try to formulate, and that's all with you experts, right? So you have the best decision to formulate. You might know that modeling this as a predictive problem does not work. Finding this is what works. So that's all with the expert knowledge. Once formulated, everything can be automated today. And then once automated, we have to look at the results, right? So, and this is my favorite, right? So none of this is God or machines. So it makes plenty of mistakes, and these things are getting better and better. So in the left side, you can see a person which became viral recently was using AI agent OpenClaw to filter unwanted, unnecessary emails, and it ended up deleting all the emails. So the person was saying, "Do not do that. Do not do that." It was not listening at all. And after it has deleted all the emails, it said, "Sorry, I did a mistake." Right? So all of this is possible because, of course, these are numerically translated problems trying to predict something. So mistakes are definitely possible. So we should use this in a way that you should be the person who is directing it, rather than that particular tool trying to take you with it. Right. So that's sort of the things. And to conclude, last two slides, another use case which is getting popular is automating operational processes in the entire healthcare domain, right? Be it a pharma company or hospital or anything. The best beauty of all these tools, AI tools we have, is we can connect all the apps to it, right? So these days I have everything configured in my cloud. I just say that, hey, tomorrow find a 3 p.m. block, and then it figures out automatically a calendar slot and it sets up an invite, and I don't even go to my calendar and do it. So a lot of scope of AI is out here, where a lot of processes that are too mainstream can be automated, so that doctors can they can focus your time on much more important things, rather than on these mainstream things. Yeah, I just concluded my 40 minutes. So I stop here and open to further questions and discussion. Thanks.
Thank you, Dr. Mahesh. It was a fantastic and very easy to understand lecture. So just before we go to the questions, I mean, I just wanted to try and summarize what I understood, so that we take away the take-home messages from this. So traditionally, in medical literature, we have been used to the conventional statistics, the inferential statistics, where we are following sort of rigid distributions, either be it Gaussian distribution or binomial distribution, whatever it is. So, for example, if we take height versus weight, and if we keep plotting them, so we know we can draw a line through it, which is what you refer to as linear regression. So as human mind, cognitively, we are able to understand parameters of 2 or 3, and beyond that, it becomes cognitively quite difficult for us to see. So by using this machine learning algorithms, you're trying to look at a data point multidimensionally in a lot of, at times even up to 100, 200 parameters, and then trying to see how each point is associated with a similar point or how close it is. So, and then this is how machine learning, I mean, obviously by using extensive mathematical computations, you are able to derive how a particular point, when you look at 100 different parameters, is associated or correlated with another point, and that is how close they are. Am I right in my understanding?
Yes, perfect. Very well put. Yeah.
Okay, great. So, and then what you further went on to say is with machine learning, there are at least 4 different ways, I mean, 4 different tools you could use to try and solve the problem that you want to solve. One of which you said was a supervised modeling. Another one is unsupervised modeling. And supervised modeling is where the clinician would sort of annotate a particular thing, saying that if you have this cluster of parameters, then you call this A. If you have this clustered parameters, and you call it as B. So you're telling the model to identify these parameters is A, these parameters is B. And then when you add a new sort of unknown sort of point, then it will identify which cluster it is closer to and call it as either A or B. Is that correct? It's supervised learning.
Yeah.
And unsupervised learning is where you don't give any annotation. You just let the computer figure out and then come up with, okay, this cluster is different to this cluster. It's not able to tell what exactly it is, but it is going to tell you that these are different. Is that correct?
Yeah. So mostly like I'm not teaching the machine. I'm let the machine figure out itself. Yeah.
Correct. And then you went on to talk about the CNNs, so deep learning neural networks, which obviously has been slightly over my head. But what I understand is these are more complex methods by which you can read the non-structured data such as voice, text, and images. And you have clearly showed the pixelated 8, suggesting that this is how the computer is going to read various sort of elements of a picture and trying to correlate or understand how it relates to its previously learned data or learned information that it has already got, and then come up with some answers. So I hope that's all that we talked about. And then the other question, not the question, but I think this is the core of your teaching process so far. Am I right?
Yeah. And then we just discussed a case study. Yeah.
Case studies. Okay. Um, I have a few questions here. The first one is the using Chat GPT to achieve the goals that you wanted to achieve. And you have clearly showed in one of your use case studies that a model that is trained in one particular hospital cannot be applied to another hospital. And we know ChatGPT is a sort of modeled on universal data which is available in the internet. How good is it in using our day-to-day or solving our day-to-day clinical problems? As we very well know, it is not modeled on clearly healthcare related data.
Okay. Yeah. Good question. So it depends on the type of use case, right? So if we are using ChatGPT, mostly, let's say, documentation or automating some process like calendar or queuing patient, appointment, something, then fine, because that particular use case is fine with the general world knowledge, right? But if we are using ChatGPT for something else where something related to medical domain, let's say the generic medicine name or some codes which are exclusive to the domain, then definitely as it is, it cannot be used. But the good part is this is where fine tuning as a concept comes, where I can build, let's say, my own chat GPT as a hospital or something using so much of data over the years I have, but I cannot achieve the general knowledge that the existing chat GPT has because my world of data is only my hospital documents. On the contrary, ChatGPT has the best general knowledge today, but it just does not know my hospital language or something. So what we can do is I can take the general knowledge of ChatGPT and do something called as fine tuning and share all my hospital data as a sample so it can adapt to it, because teaching a local model general knowledge is much more difficult, but teaching a model that has the general knowledge, just some local knowledge, is much more easier. So directly in those type of use cases, we can't use ChatGPT, but today even OpenAI, they give this option of fine tuning where I can literally upload a bunch of my local documents as a institution. And now afterwards, it takes a day or so. And then if I chat, it knows that language. But sometimes there could be privacy issues, right? Some institutions does not want to share data. It's a regulated environment. So even there, thanks today to the open source community, we have open source models like Meta has Llama from Facebook, and then there is DeepSeek, right? So there are many open source models where we can literally download to the institution's own server or machine and do this fine tuning. So we don't have the risk of sharing data to the outside. The only disadvantage in this approach is it's not so easy as an UI where I drag and drop those PDFs and that learning happens. This might be a bit technical because it's open source. But if I'm okay with sharing some data, let's say, in that case, it's as easy as me dragging and dropping, and then that adaptation happens. So long story short, ChatGPT as it is, no, but with some teaching, definitely yes.
Sure. I think one great point of concern is when you ask ChatGPT, it comes with such a confident answer. I mean, anyone has to believe it. Have you got any tips to try and reduce this? I mean, are there any safeguarding elements that we have to consider before? Because it's only a matter of time before we all take this up. And we shouldn't be falling into the trap of believing whatever it says.
Sure. That is true because these models, when they are training with samples, they are trained to please the user. That's how it is. So that's why we see whatever we say, it says interesting point, awesome view, and all right. So one thing personally, what I do is there is this all these LLMs, right? ChatGPT, Claude, or any LLM that we have today. Let me just switch screens. So all of them actually have something called as a playground. For example, I just typed OpenAI Playground. Okay, so this is OpenAI Playground. I just typed OpenAI Playground. I get this in Google. So this is ChatGPT only. Same login I use for ChatGPT, but just that here I can customize. So what I can do here is, here you can see a developer message, right? So if I just say hi in the right side and hit enter, it says, hi, how can I assist you? That's what it says. But if I give an instruction, for example, say, I say that, say thank you 10 times. If I give this instruction, then I chat, actually, it actually strictly follows whatever instruction I have given. It says thank you 10 times, right? So what I personally do is, I go to these sort of playgrounds. It's there in Gemini, it's called Gems. It's there in OpenAI, it's called Playground. It's there in all the tools out there. I go there, I put a strict message here. Like, for example, strictly refer to published resources. For example, I'm just making this up, and be very honest, be very critical with me, don't please me, don't try to comfort me. I have a set of instructions. Then I do this chatting. Actually, you can see that it's not solving, of course, but it's much more better because it takes grounding. It doesn't suggest you things. It always looks at only those references and tries to talk to you. So this is one way I personally handle it, and I find it useful.
Okay, that's great. I mean, just going to some of the questions that we have from the audience. Question I could see is, how do you differentiate these examples from complex maths? How is it machine learning and not just complex mathematics or statistics?
Okay, so it's actually a very, very thin line. It's whatever that we are seeing is it's of course foundationally mathematics in the back end. Just that, as you very nicely put in the beginning, it all works. It's very nice as long as the data is in a nice Excel file with 3 columns, 4 columns. But it just goes beyond a human math capability if it is like hundreds and thousands. So that's where these machines are coming. So in my personal opinion, it's just directly math statistics, just positioned in different particular names. Yeah.
I think it's
yeah.
Sorry.
Good. Yes, yeah.
I think it's the scale with which we're dealing is what determines, because if it is 1 or 2 variables, we are absolutely happy. And if it is 100 variables, it's impossible for us to do it. So it's absolutely, as you're right, it's complex mathematics and statistics, but at a much larger scale is how I see this.
Right. I have a few questions with your permission.
Please.
Previously, there are 2 interesting questions which I observed. Can we build our own LLMs? Adding multiple layers, will it improve the efficacy? Are the 2 questions which are very interesting. Probably Dr. Mahesh, you can just throw some light on that.
Sure, sir. Sure. Thank you. So that's where I'll take here, maybe some of the clinicians you have already worked with this. This could be redundant, but for some it could be new. So there is this data set called Mimic 3 data. Okay, so the published work that I told was on this. It's an open source data. We can just Google Mimic 3. There's a full form for this, intensive care something. So this data is about one particular hospital. You can see here, this particular hospital, between 12 years of data almost, right? And you have all the data, EHR records, the text comments given by the doctor, everything, right? Image, text, whatnot, all sorts of data is here. Now, going to the point, can we build our own model, right? Definitely yes. The same, I can put all these, I can go to this website, download this data, and I can, it might have GBs and GBs of text documents of different patients, 100,000s of patients, and I can build my own model. So I can just ask, a patient has this blood pressure, this thing. So what could be a diagnosis? It can give me a write-up. It's all possible, right? So, but the only problem is doing it this way, I will lose the breadth. It has the depth. So it has a very good knowledge of my hospitals and technical details. But somewhere in the internet, someone wrote a very nice published paper about how, let's say, smoking causes cancer. let's say that knowledge could not be useful here. So how I would personally look at building a model, my own model, is I will take these available popular models, OpenAI, Claude, or Gemini, or what, all of these, right, which are trained on the entire internet. I'll take them as a base, and then I will provide all of my own data and build my model. If I try to build my own model from scratch, I personally feel that none of us might have as much data as these giants like Google and those things. They have the entire internet with them, right? So I might lose out on quality. Rather, I can take those and try to build the depth. That will be a best approach. So long story short, yes, definitely possible. There are nice, interesting research papers we can see. They have tried to customize existing models by providing additional mimic 3 text data and trying to create like AI doc, something like that. Many interesting such works are being done. Yeah.
So there is this one fascinating question, which is many AI models are black boxes. How important is its explainability in clinical AI? Because we're going to hopefully act on the recommendations, and you do not know exactly what happened in the black box. So where do we stand?
That's really a good question. So to draw parallels, I worked few years in the finance domain, and it's very regulated. So when I'm trying to make a decision whether to give a credit card or loan to a person, a machine might say, yes, this person will definitely pay back, credit worthy. But I have to go to RBI or some central banking institution and explain why I'm giving a loan or why I'm not giving a loan. I cannot tell to RBI that, hey, machine told me yes. So even in these domains, even though I have much more greater accuracy of performance, I'm letting go these black box models because explainability is the priority here. Very similarly here also, the use cases that we should be doing, option one, it should be a use case where we do not expect explainability, or it should be a use case where it's a support system, a decision support system. It just gives a recommendation, but we have the human expert there applying their knowledge to do it, right? So in these sort of domains, those are the use cases we should target, and there is no other solution, I would say. We have to let it go and only prioritize those use cases where explainability should not be automated. That's a concern. Point well raised.
Thank you, Dr. Mahesh and Dr. Pani. We came to end of a very interesting session. Most of the questions were already explained during the lecture because we started seeing some questions, and during the class itself, most of them were answered. Few of the questions, if they were not answered, probably you can listen to this session again. I know that around 8 to 10% of this class was repetitive sort of, because we want to touch upon those things to build the new things. So that's one of those things. And just to request all the listeners and audience, please do not post attendance and quotes here. This is, if you want, there is a separate YouTube video uploaded on how to download your personalized Guinness World Record. So don't please try to spam less the chat box. Over to you, NBMS, and the feedback form will be open now, and once the live video gets finished. Thank you, Dr. Mahesh, for a wonderful lecture. Thank you, Dr. Pani, for moderating it in as lucid terms as possible. Thanks.
Thank you, Dr. Pani, and thank you, Dr. Suresh. Yeah, really
Thank
loved
you.
it.
Thank you both. It's been a pleasure.
Thank you all for joining us. Thank you.
Bye-bye.